All right. So I'm going to talk about fine-grained complexity. All right. So the subject of algorithms design or modern algorithms design can be maybe divided into two periods. The first one, maybe starting around the 1970s, was about P versus NP. So given a problem, you want to know whether it is in P or polynomially solvable. There is an algorithm that runs in polynomial time, or whether it is NP hard. And if it was in NP, then people maybe thought that was good enough, was easy, right? We're happy. As the second time period, starting around the 2000s, then we have a new demand because inputs become increasingly bigger. So the area of big data. Now, just polynomial time, maybe not good enough, right? So algorithms with polynomial time might be slow in practice. Okay, so what do? We go over those many problems in P, and we try to find faster algorithms. And the issue is that progress is stalled in many of those problems, right? We try to make progress, we can, and then we would like to know why. We'd like to explain that lack of progress with many of those problems, and I can list a couple of reasons. One is that if there's a very good reason for why we cannot make progress in a certain problem, then maybe we would like researchers to do other things and not tackle this very difficult challenge. And another reason could be to change the model. So if there is a problem in practice, right, that is typically being modeled in a certain way that now we think is very difficult, maybe we should try remodeling the problem, model it differently, maybe to another, in another way, so that we can circumvent that hardness. But how can we prove that some algorithms are unlikely, that breaking maybe n squared is not something that we should hope for? One way to try is maybe to try to mimic NP hardness, right? So SAT was proved to be NP hard, and then reductions, people showed reductions from SAT to many other problems. And then the conclusion was that breakthroughs in those problems, so faster algorithms for those problems, would imply big breakthrough in that field, right? So finding a canonical problem and then show consequences by reducing it to many other problems. And so you think maybe you can do something like that with problems in P, find a problem and then somehow reduce it to those other problems in P and show that progress in any of them would be kind of consequential. And the issue is that no such problem is known. P, and this is where fine-grained complexity enters the scene. the motivation is to simply classify the time complexity of the central problems in P. And the way to do it is by picking a number of problems, maybe a handful, just a small set of problems that we think might be difficult, and then show by fine-grained reduction, by subtle reductions from those problems to arrive at those conclusions. Like to say that if you make progress in those central problems in P, you would still break something. It would still mean something in. So just very briefly, these are maybe the central hardness assumptions in finite complexity. You can see the SETH here. For example, the strong exponential time hypothesis, which roughly speaking states that SAT requires 2 to the n time. You want to solve SAT, you have to spend 2 to the n time. So not just exponential time, but it also gives you the like how much time you should spend, concrete, roughly 2 to the n. And then assuming that, you can show hardness for many problems. For example, eddy distance. Right? You can show that to solve eddy distance, you need to spend n squared time, assuming the SETH. You have APSP, all per shortest paths, and then we have reduction to many other problems from that, and similarly threesome. Okay. APSP. Yeah. So given a graph, you want to find the shortest paths between every pair of nodes in the graph. The graph is weighted, and then the time that you need to spend is n cubed, right? And assuming that, you show hardness for many other problems. For example, finding a triangle of negative weight in such a graph would require similar time in cube. Okay, and so the way that it now works is that so we try to find faster algorithms for a long time for a problem. Maybe we have some insights about why it is so difficult, and then we can use those insights to try to show kind of formal conditional lower bounds for the problem. So they like maybe formally that they're quite difficult, but also vice versa, right? Now you try to show conditional lower bounds for a problem, you don't succeed, then you have some algorithmic insights, right? You go back to the algorithm, to the problem, then you can design faster algorithms. Yeah, and this is the way that it is. Now specifically for problems of interest. So what are central problems in graphs? We have the shortest path problem. We have the maximum flow problem, right? So matching, global minimum cuts, classic problems. I dare do that. Specifically, I focus on the maximum flow problem. So given a graph, we have the capacities on the edges. For example, with, from A to B, the capacity is 5. We want to know what is the maximum amount of flow that can be shipped between a pair of nodes. So from S to T, right? So to give you some intuition about this problem, let's see a very simple way to find the maximum flow. So we try to ship 5 units of flow from S to T along that blue path. And then after we ship this flow, we update the capacities. So the edge from A to B is now fully saturated. We cannot ship more flow along that edge, but the edge from S to A, we can ship 2 more units along that edge, right? And so we keep doing that, keep shipping flow along paths maybe. And then at some point, we cannot do it anymore. There's no more path to ship flow from S to T. And then the value of the flow that we shipped so far is the maximum flow. And by the min cut max flow theorem, this is also the value of the minimum cut from S to T. So the minimum number of edges, or the minimum weight of edges, like if you remove them, you disconnect S from T. Okay? Now, even more specifically, problem that I have focused on a lot is called the all pairs maximum flow problem. So similar to all pairs shortest path, where you have shortest path between a pair, and now you have all pairs. Now you can ask same thing about max flow. You have the maximum flow between one pair. You want to know the maximum flow between all pairs. Right? It's n choose two values, right? It's not just one value or cut. It's n choose two. It's n squared value. So given a graph, you need to output for every pair of nodes what is the maximum flow between. Okay. Now this problem is arguably interesting for a number of reasons. It is a subroutine in many known algorithms for central problems like the TSP, K-cut, so forth. It is also of practical use, right? It has been used for image segmentation and other problems in practice, social networks, and so on. Theoretically speaking, maybe we can think of the comparison to the all pairs shortest path problem. Okay, so why? So another reason why this problem is interesting. So if you think about the shortest path problem, algorithms for this problem, for the shortest path, are quite simple. You can think of the Dijkstra algorithm, for example. They're relatively simple, and okay, and they typically output more than you ask for. So if you ask for the shortest path between one pair, you get single source all sinks. You get n-1 values for free, right? So this is the situation in single pair shortest path. But with maximum flow, this is not the case. Algorithms are very complex, and you don't get that extra answers. You just get the value that you ask for, just one pair. So it seems like maximum flow is more difficult, maybe, than shortest path. If you focus on a single pair, and then you can ask, okay, if you go from that to all pairs, is it still the case? Is all pairs maximum flow going to be more difficult than all pairs shortest path? Right? Okay, so in most of the remaining talk, I'm going to focus on how fine-grained complexity tools can help us design faster algorithms. Okay, I'm going to focus on all pairs maximum flow on that problem I just described, on a specific setting where you have a very elegant data structure, right? So you want to know the maximum flow between all pairs of nodes. So if the graph is undirected and the capacities are on the edges, then Gomory-Hu showed that there is a very nice way to represent those values, right? So what they showed is that in this specific setting, right, again, undirected graphs, edge capacities, there is a tree on the same set of nodes as the given graph, so that the maximum ST flow in the tree, or the minimum ST cut in the tree, is also a minimum ST cut in the graph, right? So for example, let's say we have a graph here on the left, and on the right we have its Gomory-Hu tree. And let's say we want to find the maximum flow between two nodes, 2 and 7. Okay, circled here in red. So instead of going like computing it on the graph, we just go to the tree and we find the minimum cut between them there, which is very easy to do because it is just the lightest edge on the path between them. That is the minimum cut. So in this case, it's going to be the edge 5, the edge with capacity 5 in the tree. And so we know the maximum flow between 2 and 7 is of value 5. And we also know that here is a cut witnessing that value, right? If you take that edge 5 and you remove it, because it's a tree, you get 2 parts. You get a separation of the nodes of the graph, which is of that value. Right? This is the definition of Gomory-Hu trees. So the fact that they exist is not trivial at all. Gomory and Hu showed that in 1961 that they exist in that setting, but they also showed how to find them relatively fast. So they showed an algorithm with running time n, number of nodes, n times T of m, the running time of a single pair maximum flow, right? T of m, maximum flow. If you run n times the time of maximum flow, you get that tree. That's what they showed. Okay. And this time bound was the fastest that was known for almost 60 years. And I'm going to now tell you about the journey that we took in order to improve on this problem. Okay? Any questions? Okay, so in the first step, we wanted to think about the Gomory-Hu problem. So we wanted to know what is difficult about that problem. But we couldn't show anything for that setting, for undirected graphs and edge capacities. So what we did in order to still get some idea of what might be difficult about this problem, we went to more difficult settings. So settings where Gomory-Hu tree doesn't exist, okay? And what we showed, for example, for directed graphs with edge capacities, we showed that the naive algorithm is the best you can hope for, likely, right? So n squared applications of maximum flow, this is what you can do if the graph is sparse. So we show the conditional lower bound of n cubed, assuming this hardness assumption that I mentioned before, the SCTH. Right? If you assume that solving SAT requires 2 to the n time, then solving all pairs maximum flow in this setting is difficult. So settings where Gomory-Hu tree doesn't exist, those are the settings where lower bounds were shown. Specifically, the n cubed here was shown for directed graphs with edge capacities, also for undirected graphs with node capacities. And some of those harder settings we showed. So it depends if the graph is sparse or dense, the specific time that we showed. But this n cubed was shown for these two. Yeah, we also had results for dense graphs, but those results were a little restricted. So if we assume that we can only use combinatorial algorithms, right? So algorithms that do not use fast matrix multiplication methods, then also we had similar conclusion, right? N squared applications of maximum flow is the best you can hope for. Now I put here the asterisk because there are some noises that maybe this assumption is now broken, right? But let's leave that aside.
What assumption?
That if you restrict yourself to combinatorial algorithms, you cannot break n cubed. Like if you want to find maybe there's a triangle in a graph or solve multiply 2 matrices one with the other, the assumption was that you have to spend n cubed time if you with combinatorial algorithms. Now maybe that's not the case. There are some noises. It's not published, but yeah. Yes, you spoke about it last week here. Yeah, yeah. Yes. It's just combinatorial here. Okay, so the second step, we focused on the Gomory-Hu tree problem, but we allowed ourselves to use non-deterministic algorithms. Okay, so this is not the standard model where you, right? You can use non-determinism, and what is non-determinism here in this context? So those algorithms can make guesses, right? And then given a guess, there is a standard deterministic algorithm that produces either a correct output or I don't know, right? But we also require that for every input, in this case, for every graph, there is a correct guess. So there is maybe a Gomory-Hu tree that, okay? So what we showed is a near linear time non-deterministic algorithm for Gomory-Hu trees in simple graphs, right? So the graph is simple. So you don't have parallel edges between pairs of nodes, and the weight of every edge is just one. So again, a way to try to tackle that problem. So yep. Yes. But you also have to verify that. Yeah, exactly. Yeah, you wanna verify. Yes. So for example, if you let's talk about the maximum flow, right? You're given a graph and you just want to find the maximum flow between a pair of nodes. You can guess a cut, you can guess a flow, but just one of them is not enough because you don't know if it's the optimal one. But if you guess both of them, then and you verify that they're actually feasible, then you can say, okay, it's the same value, so I know this is a way to verify it very fast. So this is an example of non-deterministic algorithm for a problem. Okay, so we show a near linear time algorithm, non-deterministic again, and then following a known framework in fine-grained complexity, we got an irreducibility result. We got an irreducibility result for Gomory-Hu trees for this problem. What does it mean, an irreducibility result? So, so given a problem, you might hope that you could show strong conditional lower bounds for that problem, assuming the popular SETH. You might expect to show very good conditional lower bounds. Now, if you have a non-deterministic algorithm that is fast, then this essentially said that this is unlikely. It is unlikely that your conditional lower bound will surpass the time that the non-deterministic algorithm gives you, right? This is a known framework in fine-grained. We get that. So now, given that, we wouldn't try to show conditional lower bound assuming the SETH. This is what it essentially means. Now, for this problem, importantly, what we got, again, in the non-deterministic setting, is that the difficult thing about Gomory-Hu trees is just finding the values from a single node. So if you so the Gomory-Hu tree solves all pairs max flow, right? This is data structure for the all pairs variable. But the algorithmic insight that we got is that it is, as far as algorithms, it is essentially equivalent to just finding the max flow values from a single node. So single source, all sinks, max flow. This is where we should focus on. This is where the hardness lies. Okay. Again, in the non-deterministic setting, just making sure, but still, it's we thought it could be valuable. Okay. Now I'll say that as a side note, yeah.
So what we do now? Reduction of all source.
Yeah. So the way that we solve this problem, right, in the non-deterministic setting, I mean, we applied non-determinism obviously, but what we actually needed to solve is just finding the flow from a single source. That was actually what we did, right? There were some other moves, but it gave us this insight that maybe also in the standard setting, we should focus on that. Maybe that is where where we still didn't have faster algorithms. Maybe also there we should focus on that. It's just a guidance. It's not as far as that. Yeah. Okay. And so like I started to say, as a side note, later we designed a fast non-deterministic algorithm for all pairs max flow also in harder settings, so where Gomory-Hu tree doesn't exist. And we do hope that it would similarly lead to improvements later. Right. Okay. So in the third step, what we showed is that this algorithmic insight that the single source max flow is where the difficulty lies. We showed formally that it holds also in the standard model, right? So now we talk about just algorithms, not non-deterministic algorithm, just algorithm. Showed an equivalence. So what we showed is that solving all pairs max flow, so finding the data structure for all pairs max flow, if it can be solved fast, then also finding single source max flow can be solved fast. Okay, that's what we showed. So we had the guidance from tools of fine-grained, then we focused on that in the standard model, and we showed formally this equivalence, right? Single source max flow is the difficult thing. Right. So given that insight, we were able to zero in on a difficult example, which you can see here. Now, what does it mean that it's a difficult example? So this is the Gomory-Hu tree. So even if you're guaranteed that for your graph, the Gomory-Hu tree looks like this, right? You're given a guarantee. Someone tells you this is how the Gomory-Hu tree looks like. This is where P is. You have a list of the children. You have a list of the grandchildren. Even then, it wasn't clear to us for a while how to actually solve this problem, right? So you're given many guarantees. You're given a structure. You're given identity of, at least as far as lists. But what you need to do is you need to identify the actual nodes, right? Which node is where. And that was still difficult for a while. Okay? So we try to show conditional low bounds because it's triplets here. We try to show that maybe it's equivalent to finding a triangle in a graph. We couldn't do that as well. So yeah, we just got we got stuck on this difficult example for a while. And then we had the first breakthrough. We managed to get the first subcubic algorithm for Gomory-Hu tree in simple graphs. So the running time of Gomory-Hu tree that was from 6 years ago was n applications of maximum flow. And if we're talking about dense graphs, m is n squared, right? So n cubed. Now this is subcubic. This is the first time this running time was broken. And so specifically, so after we tried some time to solve this difficult example, we figured out a lemma that is now called the isolating cuts lemma. Okay. And using this lemma, so this lemma helped us get that subcubic algorithm, that algorithm that runs in time n to the 2.5. Okay. Now, two notes. The first one is that this lemma was independently discovered by another group in a different context, the context of global minimum cut. I will also say that we used expanded decomposition to solve this problem. Right, so we have a graph that is simple, right? Unit capacity on the edges, and we solve it this time. And after we published this result, several groups, including ours, used those tools, extended them, to find faster, even faster algorithms, right? You can see them here. But again, in the context of fine-grained complexity, let me say the following. So if you think about one of those faster algorithms, the one that we got here, the m plus n to the 1.9. So you see what's going on. Maybe you feel like, okay, it can go all the way down to m plus n, to a near linear time algorithm, right? This is maybe a natural thought. And what we showed by a fine-grained reduction is maybe a significant barrier to this result, to achieve this result. So what we show is that if it was indeed the case that the Gomory-Hu tree in simple graphs can be solved faster, so maybe not even in near linear time, even maybe just faster than n to the 1.5, then you can also solve Gomory-Hu tree in non-simple graphs, right? So it's a reduction. It's a fine-grained reduction that guided us that maybe we should just go and focus on weighted graphs, where right, we might as well do that. Okay. Unit capacity and also no parallel edges. Okay, and then in the final step here, together with the other group, we extended the method to general graphs, showing that Gomory-Hu tree, at least for dense graphs in the first result, can actually be solved in the time of a single pair max flow, just n squared time. Okay, this was subsequently improved to just near linear time, so an extended result for sparse graph. Okay, so questions? All right. So now I'm going to talk a little bit about the isolating cuts lemma. So this lemma that we introduced has found many applications since then. So it seems like it's useful. Here you can see a partial list of papers that used it after. And it seems like it is useful not just in all-pairs max flow or global min cut, but also other problems, other settings as well, not just edge capacities, also others. So yeah. All right, so let's go back to that difficult example. Okay, again, so we are given a graph, and we have a guarantee that this is how its Gomory-Hu tree looks like. Okay, we're given the identity of the pivot P. So we're given the identity of the pivot P. We're given a list of the children of L1 and a list L2 of the grandchildren. Right, these are the guarantee. We know the structure of the tree. We need to unveil the tree, so to speak. We need to know what are the identities of the node. You have a question? Well, I mean, if the graph is the tree, then yeah, but yeah, yeah. But I mean, it's a little degenerate. It depends on how much power you give me. But, yeah, some graphs have just one Gomory-Hu tree, some have more than one. Yeah. Oh, they are binary. So yeah, so you are also given the structure of the tree. You're just, but the goal is to know which node is where, right? Actually, identify the triplets, let's say. The capacity, yeah. But I mean, yeah. Once, let's say, if you know the identities, I guess it's more easy to know what are the capacities on the edge of the Gomory-Hu tree. Okay, so this is our version of the isolating cuts lemma. I'm not going to prove it, its full version here. I'm going to show a lighter version that is enough for this example. But you should get the idea of that now. Okay, so what does it say? What does isolating Katz lemma say? So given a graph, so you have a pivot P, and you have a set of terminals C. What it says is that it is possible to use only log n queries of maximum flow between single pairs to find an estimate of the minimum cut between P and every one of the terminals, which is going to be correct if some condition is going to be fulfilled. So if the terminal is the only terminal in its side of the cut. Okay. Now, why this is meaningful? So without this lemma, if you wanted to find the maximum flow values, you would have to go to every one of the terminals and compute the minimum P and that terminal. So let's say V, so minimum PV cut, right? Takes a lot, seeing applications of maximum flow, and that's a lot. And the new thing here is that no, it's enough to use just log n applications, and you could possibly get much more. Okay. This is the general statement. I'm not going to show it. I'm going to No. It doesn't any structure of the anything. Yeah, this is just the version of our version of the isolating Katz lemma. You have a pivot. You have a set of terminals. If this holds, so I can show an example on this example, but it's on. Okay, sorry. Yeah. What? Yeah. So can I just show the example? I think it is going to answer, but if not, then we can talk about it more. So let's say we're given. So this is, let's say this is the these are the terminals, right? You have the blue nodes here. So what the isolating Katz lemma will return for the terminal X is the correct cut, right? It's going to be those 3 nodes, because X is the only terminal in its side of the cut, right? However, for the node U, this is not going to be the case, right? You have 2 terminals in the side of U of the cut between P and U. So let's say if we had one Gomory-Hu tree for the graph, then the cut you're going to get is not correct, right? So now, can you please ask again?
Well, that's same, but let's look at the condition that's in there.
Yeah.
If for every node looks at the cut or the
Yeah.
then
No, but so even just 2 terminals, then the condition doesn't hold, right? You want that the side of the terminal has only that terminal in its in that set of nodes, right? What is so given this Gomory-Hu tree, you have the cut between P and U. You can find it. It is U, V, and that node, right? This is the cut. You have 3 nodes in one side and the rest of the nodes in the other side. So the side of U in the PU cut has 2 terminals, right? So the condition doesn't hold. The condition requires that you only have 1 terminal in U side of the cut in that case. Okay. I'm sorry, can you please repeat? Yeah. Right. So let's assume that there's just one Gomory-Hu tree for the graph. This is the Gomory-Hu tree, and there's no other, right? So if you go with this assumption, then a cut, then this would not be like, so this is the only cut for every one of those terminals. Let's say for the node U, the only cut between P and U would be those 3 nodes. Right. Okay. More questions? Okay. So again, let's assume that this is the only Gomory-Hu tree of the graph G, and this assumption is not overreaching, right? You can get it by, for example, simple perturbation on the weights. You play with the weights a little bit, then you get unique minimum cuts. So that is if you have weighted graphs, but even on unweighted graphs, you can still do it by considering maybe latest cuts, or cuts that are closest in a way to one of the nodes in the pair, right? It's not too average. Okay, so again, in the version that I'm going to prove or show you the proof sketch, I need to tell you what are the log n max flow that you should run in order to solve this difficult example. Okay. So what you do in G, right? So this is the Gomory-Hu tree of the graph G. So what you do in G is you add edges of infinite capacity, let's say U, let's call it U, between the pivot P and every one of the terminals. Now, in this example, I would pick the terminals to be the nodes in L1. All of the nodes in L1 that are given as a list, we just pick them as terminals. So we go to G, we add edges of infinite capacity from the pivot P to every one of those nodes in L1. Okay? Now, what is the observation here? Important observation is that for a node U tilde in L1, if it is the only terminal in subtree, it is, right? Then all cut members of U tilde remain in the same subtree, right? So if we think about the Gomory-Hu tree after the modification we just did in the graph, it's going to behave. It's going to look like this. The cut members are going to be the same, right? This is the argument here. Okay. And the proof sketch is that if there was another cut between P and U tilde after the modification, then we can just remove those heavyweight edges and get a different minimum cut between P and U tilde. And we assume that there's just one. Okay? Right, so after the modification, we have TM. This is how it's going to look. Now, in the second step, we repeat the following in G. Again, we repeat the following polylog n times. So what we do in G is we take the pivot, we split it in half. We have now two pivots. We have P1 and P2. We add an edge of infinite capacity U squared, so it's a little bigger even. And then I have to tell you how to reconnect those edges of capacity U from before. So what you do, simply you connect them either to P1 or P2 with probability 1/2. Okay, so you had an edge that was connected to P. Now it is connected either to P1 or to P2 with probability 1/2. Okay, just good. Okay. After you did that, you find the minimum cut between P1 and P2. And this is one step. You repeat that polylog n. Again, so we have two observations here. The first one is that TH, so the Gomory-Hu tree of the graph after this second modification, with the edge, this new edge P1, P2 constructed, is just the previous Gomory-Hu tree. It is just that Gomory-Hu tree. And the idea behind it is that this edge is so heavy, U squared it is so heavy that no other minimum cut would like to use it. It would not make sense for any minimum cut to use this heavy edge, with the exception of the minimum cut between the ends of this heavy edge. They are the only one that would like to use, right? So almost all of the cuts are going to be exactly the same. Okay, and the second observation is that all terminals that we connected to, let's say P1 in G, are going to be connected to P1 also in the Gomory-Hu tree. They're not going to be connected to P2, right? So if we connected that node, let's say, to P1 in the graph, it's impossible for it to be connected to P2 now in the Gomory-Hu tree after the modification, right? What is the reason? The reason is that otherwise, if it was not the case, then the minimum cut between P1 and P2 would have been U squared plus U from that edge that is now associated with the other side, plus something. And we already know that there is a minimum cut of value that is smaller, which is U squared plus something smaller, like the weights of edges in the graph that do not include infinite capacity. Okay. Now, what is the higher level idea behind it? Okay, so every time that we do this polylogan repetition, so in every repetition, we get a lot of information about how the eventual Gomory-Hu tree looks like, right? Maybe we don't get exactly which grandchildren belong to which children, right? But we do get, in a batch kind of a way, how roughly half of the grandchildren belong to roughly half of the children, right? So we know that grandchildren are not going to now belong to different, right, to different children. So if we connected the children to P1 and P2 in that way, we know that those grandchildren are going to go in the same side as those children, right? So we get a lot of information. And what we also know is that for two nodes in L1, right, in at least one of those repetitions, they're going to be separated. They're going to belong to different pivots. So using that information, what we do, for every terminal U tilde in L1, we define S U tilde to be all of the nodes that went with their parent in every one of those repetitions, right? And this gives us the Gomory-Hu tree, this example. Do you have any question about what? Yes, please. Yeah, this. Oh no. So this process. So we had the first modification here of adding edges of infinite capacity. We do this separation of P to P1 and P2. We get a separation of the nodes of the graph to 2. Now this specific step we do polylogan time, right? So we don't run it on the result and then continue polylogan time. We just run it on the result of the first modification. So on this graph. Maximum flow we compute. We get a minimum cut. In every iteration, we get a minimum cut, right? So we have log n iterations. In each one, we computed the minimum cut between P1 and P2. We get a separation of the nodes, and then eventually we have the sets. Okay. More questions? Right. So if you're asking about the actual lemma, eventually we don't really use infinite capacity edges. We don't really. I mean, it's a little different, but I think it's a constant log n times. You don't really need a redundancy. No, it's just for simplicity, for me to be able to explain, hopefully, good and fast. Okay. You're talking about the actual lemma, or yeah. Right, but so what I did here is I have a list of the nodes in L1, and I told you to just connect it to all of them. And now the condition is a little degenerate, right? Because it's obvious that it's going to hold. But essentially, this is how you run it. Yeah, you're just going to get many false results in graphs, right? If it is not the restriction. But this is how the restrictions is relevant. The restrictions are mostly. Yeah, right. So in the remaining time that I have, a little bit, 5 minutes. Okay, so I'm going to go briefly about two other results that are connected in a way. So the first one is a paper from a couple of years ago. It's about extremal combinatorics. Okay. So what we showed, we defined a new concept. We called it bridge girth. And we show that it is connected to many problems in extremal combinatorics. Now, what do I mean by that? So in extremal combinatorics, you have many problems. Some of them are oracles, undirected graphs, directed graphs. There's a lot. And then typically the goal would be to find bounds for sizes for objects that satisfy those problems, right? You want to know what is the extremal bounds for these problems. And typically, one might say that proofs are in a way ad hoc, right? You want to show that there's an upper bound for a problem, you look for a way, then you figure it out, and you're happy. Now, there's one exception for what I just said, which is graphs of high girth. Now, what is the girth of a graph? This is the smallest number of edges in a cycle there, right? So it is known that for some of those the sizes of some of those objects can be described by the size of graphs of high girth, right? For example, the size of I don't know, spanners with a certain stretch can be related to the size of graphs of high girth, right? This is known. But for directed graphs, this is not really the case. There was not really maybe a unified notion, right? If you try to think of directed growth, so directed cycle in a graph, then it is quite degenerate, right? You can have graphs that are very dense without any directed cycles. For example, a bipartite graph, right, with all of the edges directed from one side to the other, it doesn't have any cycles, right? But it's very dense. So yeah, what we did was we defined bridge girth, and we define it in what is called a path system. Okay, this is essentially a directed hypergraph, right? So you have vertices and you have ordered subset of vertices. This is a generalization of directed graph. So if all the subset of size 2, this is just directed graph, and the size is simply summing the sizes of the paths, right? So right, this is an example of path system, right? A, D, F. This is one ordered subset of vertices. Yeah, and so what is a K bridge? Right? It's a pair of K nodes and K paths that contain certain pairs in order, right? So you have one unique pair, which is 1 and K. We call it the river. And then you also have K-1 paths containing pairs of nodes in a sequential manner, right? So 1 and 2 are going to belong to one path, and then 2 and 3 are going to belong to another path, etc. So for example, here you can see 2, 3, 4 bridge, right? So you have the river, which contains those two nodes in order. There might be other nodes in between, before, after. And then you have the arcs, right? 1, 2, 3. It's essentially a cycle of paths with one path flipped. This is essentially the concept that we define. And then similar to girth, the bridge girth of path system is the smallest integer for which S has a k bridge path system, right? Just like in girth, we define it here. So this example on the left doesn't contain a two bridge, but it does contain three bridges, right? You have A, E. This is the river here, and then you have this path A, B, F, and B, D, E as the arcs. And we define beta and pk to be the maximum size of the path system without k bridges. Okay. And then what we showed is that many of the problems here that are more of with the directed vibe kind of, they are connected to high bridge girth systems, right? Their sizes can be written with beta as a part, right? So just to give you an example, we have reachability preservers, right? So RP and P, you have N nodes, and P pairs, you want to preserve reachability in the graph. With our new concept, we're able to improve on the upper bound for reachability preservers with those parameters because it is connected to the size of beta NP infinity, which is bounded by beta NP4, and then we have this bound on beta NP4. So this is an example of how it works. Why it is good is because if you improve the bounds on what we define as beta, you get several improvements at once, right? It also kind of simplifies the map, similar to fine grain maybe. Maybe that is kind of the connection, and also simplifies maybe existing proofs. Now, finally, I want to say just a few words about this new result. It is accepted to this stock 25. So this is about a new algorithm for global minimum cut, right? You're given a graph, you want to remove things, maybe edges, maybe nodes, weighted nodes, so that it is going to become disconnected. But you want to remove the least amount of things, least weight, least things. Okay, so what was known is that with the exception of vertex capacities, all versions can be solved faster than this conceptual bound of Mn, of n applications of maximum flow, right? Everything could, I mean, we knew how to solve it fast, but not for vertex capacities. For vertex capacities, the fastest algorithm before our work was Mn, n applications of maximum flow, Henzinger, Rao, and Gabo from 96. We were able to show Mn to the power of 0.99. We're able to break this conceptual bound. It's not going to be used in practice, but we believe it's very, it's of importance in theory. Yeah, now finally, those are my interests, I would say. I care deeply about fine-grained complexity. I also care about problems in graphs. Maybe you can see some of them here. And